Okay, so welcome back. Today we have Professor Bedangadas Mohanty from NISER, Bhubaneswar, going to talk about search for dark matter in underground laboratories. Just a brief, bio about Bedangadas. Of course, he's a very accomplished and distinguished speaker. I don't think I'll be able to do justice to introduce him fully, but let me take just a minute or two to just highlight some of his achievements. He's a professor of physics and dean of faculty affairs at the School of Physical Sciences, NISER, Bhubaneswar. And recently, he was also a scientific associate at the Experimental Physics Division, CERN, working on ALICE. He is a member of the SuperCDMS collaboration for dark matter search, about which, of course, he's going to speak today. Bedangadas did his master's from Utkal University, Bhubaneswar in '96, and PhD from Institute of Physics, Bhubaneswar in 2002, and postdoc at the Lawrence Berkeley National Laboratory, US, LBNL. He was, before joining NISER, he was at the Variable Energy Cyclotron Center, VECC, Kolkata, for almost 10 years from 2002. Bedangadas won many awards and honors for his academic excellence. I don't think I'll be able to list all of them. Just a few. J.C. Bose National Fellowship in 2017, and Fellow of all three National Science Academies also in 2017. Bhatnagar Prize in 15, Swarna Jayanti Fellowship in 2010 and 11, DA Outstanding Research Investigator Award in 2010, DA Young Scientist Award in 2006, INSA Young Scientist Medal in 2003. As I said, just only to name a few. I couldn't really go down much in the list. There are many more. He's currently the editor of International Journal of Modern Physics, E. So with these few words, I request Bedanga to start his lecture today. Bedanga.
So thank you, Dr. Satyanarayanan, for giving this opportunity to share something related to dark matter physics, which I have just a few years back entered, so that I can gain experience in working in an experiment, and maybe we can have an experiment in India when the Diano facility comes up. So the title of my talk is Search for Dark Matter in Underground Laboratories, and the outline is as follows. First, I will give a introduction to dark matter. What are the astrophysical evidences? 3 of them I will discuss. Then we will discuss about properties of dark matter and its candidates. Then I will only focus on this weakly interacting massive particles, its detection, and how cryogenic dark matter search experiments generally work. Since we have not yet found any dark matter candidates, that means we have to work further to make some novel detectors to increase our sensitivity. One such idea I will share. Then we will have a brief look at possibilities in India, and then I will summarize. I've tried to keep it at a level of a general audience, so some of them you may find it to be quite general. And at the end, last 4 minutes, I'll try to play out a rap which I came across in this dark matter, which will also tell us about the history of dark matter. So let me move to the next slide. This slide discusses about the energy and matter budget of the universe. And the one which has come out recently from Planck collaboration is shown here. And that tells us that all that we see around in this universe, or the ordinary matter, is roughly, or is about 4.9%. Then the dark matter constitutes 26.8%, and the remaining is what is called as dark energy. Today's talk focuses on this 26.8% dark matter. Now, just a brief idea about how Planck got these numbers. Usually in such experiment, one tries to measure or detect the cosmic microwave background radiation. That is the perfect black body radiation. It's a landmark evidence for the Big Bang theory of origin of universe. Measuring that, we know that the temperature of our universe is 2.7 degree Kelvin. And usually what they measure is intensity as a function of frequency. A little different variant is shown here. It is the temperature variation as a function of multiple moments. This is in a simpler way, x-axis could be in terms of angular separations. And what is shown is that this distribution has a variety of components. So for example, dark energy, dark matter, baryons, and also dark matter. So they have this data from Planck, and then they try to explain this with various contributions, and that allows us to fix this contribution from dark matter to be 26.8%. Now, are there any evidences that such a dark matter exists? We all know in science, hypotheses often come from an abnormal observations, something that appears unexpectedly or acts in an unexpected way. So I will discuss three commonly cited unusual astrophysical observations which are credited to dark matter. One is abnormal galaxy rotation speeds. The second is patterns in large scale universe structures in universe. And third is the bullet cluster. So let me first start with discussing abnormal galaxy rotation speeds. First, what is shown in this left-hand side are the orbital speeds of planets in our solar system as a function of the mean distance from Sun. And the line tells us what is the prediction or what is the calculation from Newton's laws of gravity, where this is the mass of the Sun, and you can see it explains it very nicely. Then the next step is, can we then extend this idea to look at the rotational velocities of stars in galaxies? If we do that, then we will also arrive at a similar expression. And so the expectation is that if the stars are closer to the center of the galaxy, the speeds will be larger. And as you go away from the center of the galaxy, then one would expect that because the gravitational pull is less, so the orbital velocity will be slower. But that is not what was seen in observations in early 20th century. This is the velocities as a function of distance from the center of the galaxy. And here is the data points, whereas the expectation, especially at large distances, is way off. So we expected it should be slower, and what it turns out to be is much larger. So that one of the immediate consequence of that maybe there is a lot of non-luminous matter around, and that leads to this deviation from Newtonian expectation. And that first coined, or thus became the first such hints of existence of dark matter. Now let me move to the second observation. At the moment, we know that our galaxy is Milky Way, and there are many such galaxies which form clusters of galaxies. Clusters of galaxies form superclusters. We know that today we know that the clusters of galaxies are made up of galaxies, hot gas, and dark matter. Now, how do we know about it? We actually use a very interesting technique which is called as gravitational lensing. This has a direct analogy to the deflection of light by lenses in optics. And what it means is that somehow a large amount of matter acts as a large magnifying glass. For example, you are trying to have observations at Earth, and you are trying to look at something beyond this cluster of galaxy. This acts as a lens, and if suppose the object is in the line of sight, then because of general theory of relativity, we know that the lights could bend because of general relativity. And then this object that you see, you can, because of this lensing effect, you can see these 4 different structures, and then you can locate and find out the objects in the universe which is beyond the cluster of galaxies which is in the line of sight. Actually, this was that the general theory of relativity works was first pointed out by Arthur Eddington, and he wanted to popularize this to people that it's actually working. So he used to tell a poem here, which I have just quoted. It's interesting to read. Oh, leave the wise our measures to collect. One thing at least is certain, light has weight. One thing is certain and the rest debate. Light rays when near sun, a massive object, near sun, do not go straight. So he used to tell this to popularize that it's actually things, general relativity is at work. Now, one such interesting cluster is the bullet cluster. Now, this bullet cluster is a cluster of galaxy which is formed due to the collision of 2 galaxies. So when 2 galaxies collided, the matter slowed down. The gases, hot gases get heated up. As a result, they emitted bright X-rays, and that's what you see as red in this picture. Now, these are very close to the center of the collisions. What you see is matters which are much farther away from the center of the collisions. And that is what is called as evidence for dark matter. It just seems that the dark matters associated with the 2 galaxies crossed each other unimpeded and went to the different zones here away from the center of the collisions, suggesting that they do not even have a lot of self-interactions. So this was the first bullet cluster which was seen, but subsequently many such bullet clusters were observed and this evidence was solidified. Unlike the galactic rotation curves, this evidence is independent of details of Newtonian gravity. It's considered as a direct evidence of existence of dark matter. Now let me go to the third evidence. Now when the universe was young, it was very hot. It was made up of charged nuclei and electrons, and photons could drag these particles and prevent growth. They were the mediators of the electromagnetic interactions between these nuclei and electrons. But dark matter was immune to this, and with the help of gravity, it began to form structures. And when universe cooled enough to form atoms, then what happened is that these atoms got pulled into dark matter structures, falling into their gravitational potential wells, and you see the galaxy distribution has such structures. So the originator of these structures were actually due to the dark matter. That's the idea behind this large-scale galaxy structure formation. This was corroborated by what is called as the Millennium simulations, which is shown in this bottom. And you can see the simulation, the dark matter distribution structures are very similar to that for galaxy distribution structures. So this is also considered as one of the evidence for dark matter. Now, when this dark matter was at work to make these structures, they left a signature on the sky, which is called as the baryon acoustic oscillations. It's something which resembles ripples when a stone is flashed into water. This is obtained by measuring the correlation functions by SDSS as a function of separation. And this baryon acoustic oscillation peaks are explained only if you account for dark matter. So I hope I have told you that there are 3 astrophysical evidences which are pretty strong, which suggest that such dark matter exists. Then you may ask, is there any alternate explanations? There are some ideas. 2 of these ideas have tried to explain the rotational curves of galaxies, which I discussed as the first evidence. and they do not satisfactorily explain the other two evidences. Now, what are the two ideas? Maybe one idea starts with maybe that we have missed some matter, and that's why we are not able to explain the rotation curves. What could be these matters? These matter could be brown dwarfs, burnt out stars, small or ancient black holes that are too dim to be seen. So these are called as massive compact halo objects. Now, if we have a sufficient number of this, maybe we could explain the rotational curve of the stars in the galaxies. However, widespread search has been carried out for these objects, and we did not find enough of them. One example is, as discussed in this paper, if you look at number of binaries as a function of angular separation, and you try to fit this data, one is able to, or the authors have been able to rule out presence of these matches with 95% confidence level, which are heavier than, say, 40 times mass of sun. So these are not detected, and hence, and in addition, they are not able to explain the other evidences. The second idea is maybe one can modify Newtonian dynamics, or this is called as the MOND. This theory, in a simple way, tells that Newton's laws of motion could be modified at small accelerations. And if they do that, they claim that they can explain, as you can see, this line goes through the data points of the velocity versus distance of the galaxies. However, these models are not able to explain the baryon acoustic oscillations or large-scale galaxy structures or the bullet clusters. So still a lot of work to do to explain that. So alternate ideas have not yet worked so far. Then let me come to what do we know of dark matter? One thing we know that they do not have any color charge. What are color charge? These are quantum numbers which are carried by the fundamental constituents of visible matter, which are quarks and gluons. Since they do not carry color charge, that's why they do not undergo strong interactions. One of the 4 fundamental interactions in nature, for example, interaction responsible for binding nuclei. Dark matter also doesn't have electric charge, the charge carried, for example, by electrons. Electromagnetic interactions, hence, they do not undertake. It is another of the 4 fundamental interactions in nature. And for example, the one which binds atoms. From the bullet clusters, we have seen that there is no strong self-interactions in the dark matter. From the evidence we discussed about large-scale structure formation, we know that dark matter is stable and long-lived. And there are other evidences to suggest they are cold. For example, what I mean by that is their velocities are much smaller than the speed of light. So it seems that they can interact dominantly via gravitational interactions. All these aspects of dark matter suggest that they cannot be standard model particles. Neutrinos as a candidate also doesn't work. They're not sufficient numbers to explain the evidences which I discussed with you. Now, this is what I think we know about dark matter. What are the things which we do not know? Yeah, there are things, many things which we do not know. For example, we do not know what particles are responsible for dark matter. We do not know if the dark sector is rich. For example, does dark atoms, dark molecules exist? We also do not know if dark matter always existed in the universe or it was created sometime later. Will it be eternally stable or it will decay someday? That we do not know. What is interesting is that somehow the ratio of matter to dark matter is of the order of 1/5 since early stage of the universe to the current stage. So this is what we do not know. So as a result, there are a lot of speculations as to what could be the dark matter candidates. In a sense that the mass of the dark matter candidates, you can see in the x-axis, vary by several orders of magnitude. And the interaction strengths can also vary by several orders of magnitude, starting from very tiny fraction of proton mass, like axions, to several thousand times heavier than mass of sun. The interactions could be starting from a million times smaller than neutrinos to about 10 to the power 18 to 20 times smaller than interactions that neutrinos do. One promising candidate is this weakly interacting massive particles. This idea was proposed and the reference papers I have given here, I will not go into details of that. I will refer to these publications, but this is a candidate which several people are interested in looking at, and I will be discussing more about this. So these WIMPs, let's see how one could detect possibly these particles. There could be three broad methods of detecting them. One is called as direct detection, other indirect detection, and the third is accelerator searches. I will explain in the reverse order. The idea behind the accelerator searches are, we have two standard model particles. They come and collide, and they may form dark matter particles. For example, the Large Hadron Collider is very actively taking data with increasing luminosities. So one place to search for dark matter is when the standard model particles collide, the protons collide at LHC, they may produce dark matter. And if one detects that, that comes under the accelerator searches. And the two experiments which are active are ATLAS and CMS. One thing about this mode of detection is that although we may find signals of dark matter, but to prove that there is a dark matter particle is a daunting task, because one has to show that the lifetimes are comparable to, say, the age of the universe. And that's a difficult challenge to do. On the other hand, what these accelerator searches can tell us is the energy scale. And that may help the direct and indirect detections searches. What about the indirect detection? This is when two dark matters collide to produce standard model particles. So if dark matter exists in galaxies, clusters of galaxies, they may collide, annihilate, and they can produce standard model particles. And if one can detect them, then that would constitute a detection of dark matter. Now, what are the particles we should look for? For example, general idea those doing there is to look for antiparticles like positron or antiprotons, and that is because the cosmic rays do not have very abundantly these particles that is related to the baryon asymmetry in the universe. So experiments try to look for enhanced production of positrons or antiprotons. Other promising things to look at is, for example, high energy neutrinos. And there are experiments like IceCube, Antares, who have specific scientific goals to do that. Or people try to look at high energy gammas coming from annihilation of dark matter. So those are indirect ways of detecting dark matter. What I will discuss a little bit more in detail is the direct detection that comes from the interaction of the dark matter with the standard model particle, like that of the detector material. And let me go to the next slide to discuss this direct detection a little bit more in detail. The idea that this can be done was first proposed by Goodman and Edward Witten. What they said is that the weakly interacting massive particle could interact with the atomic nuclei, and that interaction cross sections are not small. I mean, it's small, but it is non-zero. And when it interacts, the atomic nuclei could recoil, and if you can measure this recoil energy, then one would have ability to detect dark matter quickly. As you will see in subsequent slides, this recoil energies are low, definitely less than, of course it depends, I will show you the formula, it depends on the mass of the dark matter, the mass of the atomic nuclei, but it's of the order of a few keV or tens of keV. That immediately tells us that we need to build detectors which have low energy thresholds, because we are going to measure energies which are small. The difficulty is that, as you will see in the next slides, is that this interaction rates are small because it takes place via weak interactions. And weak interaction is a weak force. So the dark matter particle comes, interacts with the constituents of the nuclei through an exchange of a G boson or a Higgs boson, and they exchange energy. However, most model tells us that the dark matter and the nuclei remains intact. That means they are imparting small energies, and we are going to look for these small energies. So that is, since the interaction rates are small, that's a little bit of a bad news, but the good news is interactions does happen. Apart from this low energy threshold, one has to be very careful about the backgrounds. And I will discuss it in a little bit in detail, that we have to work in ultra low background environment, and there should be a proper background understanding and discrimination. Then, since the interaction rates are small, we may need the detectors to operate for longer times, and we may need large detector masses so that you increase the probability of interaction. But most of these cryogenic-based dark matter searches work in an environment where running large mass detectors for a long time is itself quite challenging. So let me try to give you an idea about what is the typical interaction rate that we are talking about. This is a simple way of explaining what would be the order of interactions. Generally, people make use of the standard halo model in order to arrive at numbers, and it has some assumptions. One of the assumptions is that we have a dark matter halo, and its density distribution goes as 1 by r square, and it is isotropic. The second assumption is it is made up of collisionless particles, and it behaves as an ideal gas. The third assumption is the dark matter particle velocity distributions are Maxwellian. And the fourth assumption is that there is a hydrostatic pressure which is supporting the gas against a gravitational collapse. With this assumption, you can try to calculate the event rate. Generally, we know that the event rate goes as cross-section times the number density times the average velocity, and that is what I've written here. And you can write this number density as some matter density divided by mass, and the average velocity is obtained by integrating velocity over the distribution function. The cross-section, of course, has a spin-dependent and independent part. Those are theory details. Let's look at this formula carefully. You can immediately see that a typical experiment would try to get the left-hand side. And the right-hand side has two unknowns. One is, what is the cross-section of interaction of the dark matter with the nucleon or nuclei and the mass? That, what I mean to say is, different combination of this m and the sigma can give the same rate. So there is a degeneracy. And that is one of the reasons why you see the sensitivity, the limit, the exclusion plots are usually plotted as the cross section as a function of the mass of the dark matter particle. Now let's get a typical idea about the typical numbers. Now from various astrophysical measurements, this integral is upper limit is the escape velocity, which is typically 544 kilometer per second. The local dark matter density is taken to be about 0.3 GeV per centimeter cube. And if you plot in typical values of cross sections and masses, average velocities, and that is why this lower one is expressed with some numbers in the denominator, because these are the typical numbers. If you put in these typical numbers, the rates that you get is about 0.1 event per kg per year. And that's challenging. And that is roughly the signal that you expect in the laboratory. Now let's discuss a little bit more of the challenges that one faces in the laboratory detection of dark matter candidates. If one just does a simple scattering calculation, elastic scattering calculation of dark matter with atomic nuclei, then one can easily calculate the recoil energy. And this is given in this expression. It depends on mass of the detector nuclei, mass of the dark matter, the angle. And if you again put in typical values, then one would see, say for example, let's take xenon and 100 GeV mass, and you vary theta from say 0 to 90, then this recoil energy would be varying from about 0 to 30 keV. So the first thing that challenge, as I mentioned earlier, the challenge is that it's very low. So you have to have detectors which run at low threshold. The second thing is, if you look at this rate as a function of recoil energy, you find that for different kind of target nuclei, silicon, argon, germanium, xenon, actually the rates are larger for smaller recoil energies, below 10 keV. This again tells us that one has to operate detectors at a low threshold. Then if you go to heavier nuclei, then it seems it comes down quite fast because of the form factor contributions. And you have to carefully choose what type of target nuclei you are trying to look for, you are trying to use. One underlying physics behind this is that we know for elastic scattering, the maximum energy transfer takes place when you have two particles of similar mass. So if you are doing low mass dark matter search, then you have to accordingly also choose the detector nuclei. Now these are calculations shown for a typical value of cross section and mass. If you decrease the dark matter mass, then this spectrum squeezes. So you still go to smaller recoil energies, again indicating that your detectors have to work at low thresholds. Another way to express the challenge can be explained through this curve. This is a cross section in the y-axis and mass in the x-axis. Let's assume just that an experiment has measured this distribution, this one which I'm showing through my pointer. Now, if you want to measure things which are sensitive to smaller cross section, you have to go in this direction. And in order to go in this direction, the way is to increase the detector mass, or increase its exposure time. Now, suppose you want to, this is your measurement now, you want to go and search for lower mass dark matter particles. Then one has to go in this direction, and that's possible if you have low energy threshold in your detectors. And if you also have smaller targets, it also shifts this distribution from right towards the left. So in order to plan an experiment, several things are needed: inputs from astrophysics, particle physics, nuclear physics, and detector physics. All this taken together help us to plan an experiment in dark matter search in laboratory. Now,
Bedanga, can I interrupt you?
Yeah.
There are a few questions. Is it okay if you can take at this point and then continue, or you would like to take all of them at the end?
Whatever you say. I didn't see, sorry.
Okay, no. I mean, you don't have to see. I will look for them. Okay, maybe let us take a few. If you want, you can postpone some of those questions afterwards. So there's a question from Hariom.
Yeah, sir, at slide number 11.
Slide 11, just give me 1 minute. Yes, please.
Yeah, so this right bottom, you are showing the interaction with the nucleus or some nucleon. So you are this interaction is happening via this weak interaction, right? So you told Z and W particle, but you also told this Higgs. So this kind of interaction is like our this standard model interaction or something different.
Yeah. Those interactions are possible to happen when a dark matter candidate interacts with the standard model particles. That is, go ahead.
But this Higgs, this in weak interaction we are having just 3 particles, right? W plus minus and Z.
Yeah.
So how this Higgs come?
Yeah. So well, those are details, but if I remember, I have seen that it could also exchange Higgs boson. I am noting, I can send you the reference, but I have to, I have to go through the details to tell you what is that Feynman diagram and what is the mechanism. I mentioned it because I have seen that is also can be an exchange particle.
Okay, sir.
Okay.
Yes.
Yeah, Bedanga, there are quite a few questions on YouTube. Do you like, without interruption, to go till the end and then take these questions?
Okay.
Okay.
We can have a longer discussion maybe towards the end.
Okay, that's fine. That's fine. That's why I asked. Yeah, please. Sorry for the interruption.
No. This is nice to know. People are asking. So
yeah, there are lots of them on the YouTube.
Yeah.
I think you can take that.
Try my best. I'm also learning. I'll learn from you also. Okay. Let's. Okay. Let me go through and then we'll have a longer discussion. Okay. Now coming to how can we detect these dark matter candidates or particles like WIMP? Now, there are 3 techniques. So the general idea is that we have to measure this recoil energy. So how can this nuclear recoil energy, so a dark matter particle comes, it hits the atomic nuclei, scatters of the atomic nuclei, there is a recoil, and you are trying to measure this recoil energy. How can this recoil energy be dissipated in the detector material? It can be dissipated by scintillation, that's the light. It can be dissipated through heat or leading to lattice vibrations or phonons. It can also lead to ionization, right? Where the positive ions and the electrons pair are formed, and then you can apply voltage, and then you can collect the signal. So there are these 3 mechanisms by which the recoil energy of the nuclei dissipates in the detector material, and hence the detection techniques makes use of them. Ionization, charge, scintillation, light, phonons heat. What you can see here is that in this sort of Venn diagram, okay, let me get the pointer, that different kind of experiment uses different techniques. Okay, many of the good experiment uses two of these techniques, so you can find them in these intersections. For example, the experiment which I am involved in makes use of ionization and phonons. These are the two channels which SuperCDMS uses. But what you can see is there are so far no detectors which can measure all three. And if you have an interesting idea, it's a challenge actually, where if we can build some detectors which can cater to all three, that will aid the detection a great deal. So think about it, young people, and if you can come up with a detector which has all the three channels, that would be really exciting, and that would open up new avenues in this field. Okay, so that was about the detection. I will go into more on how to detect when I discuss the SuperCDMS, how they work. But let me move on to tell that having a control on the background is very, very important. Now, what could be the background? One background could be neutrons. Why new? And that's a very, very important background. And why it is so? Because it's a neutral particle and it has quite a bit of mass. It can mimic the signal of dark matter. When dark matter, a neutron collides with atomic nuclei, it can give rise to recoil energies mimicking the dark matter signal, and the neutron goes away of outside of the detector, and hence we will never be able to find that unless you put some other detectors to do vetoes and other things. Now, what could be the source of these neutrons? There could be two dominant sources. One is cosmogenic, another is radiogenic. Now, cosmogenic, what is that process? Well, cosmic rays or cosmic muons can interact with the materials which are in front of your detector, and that can produce neutrons, and these neutrons can go and hit the detector. So what is the way out? The way out is try to stop these cosmic rays and hence go underground. This curve here tells us about the muon intensity as a function of some depth in terms of water equivalent. And the various experiments, I will later on tell you where the two underground facilities, the proposed Dayano and Jadugada lies. Later on, I'll come to it. The SuperCDMS experiment will be here. So the deeper you are, better you can prevent these cosmic rays coming into your laboratory, and hence you can control cosmogenic contributions from neutrons. The other is radiogenic, coming from uranium, thorium, 40, potassium. Now, how do we stop these? Well, these can be stopped, the reason they are there is that uranium and thorium have large, long lifetimes, and as a result, they are present. And even if they are present in small amount, remember our event rate is also very small, 0.1 interaction events per kg per year. So these sources of neutrons has to be also stopped. And one way to do that is to employ shielding. So how does the shielding happen? This is one example again from the CDMS experiment. Let's go to this on the left-hand side diagram. You have to first look at what are the sources of background, and then accordingly plan the shielding. For example, SuperCDMS will have a 60 centimeter water, and that would stop or reduce neutrons coming from muon-induced interactions. Then there would be graded lead shield to stop photons. Okay, one thing I forgot to say that if they're radioactive, materials, you can emit alpha, beta, and gamma from different sources. Alpha and beta have relatively small penetration depth, but gamma has high penetration depth. They can go and again cause backgrounds which can smear your signal. You will not have a good background to signal discrimination. So people use lead, and then, however, then this gamma could interact with lead and produce particles which will again fall in your detector and mimic the signal. So then you have to have a judicious choice of a shield of poly. Then you put copper and then mu metal. All these together has to be planned, calculated using geo-simulations, knowing the inputs, and then you decide the shielding to control the background. Background itself is quite challenging and a detailed effort. Now let me come to how SuperCDMS, or a cryogenic dark matter search experiment, detect the signals. Well, they use what is called as the solid state detectors, either a silicon detector or a germanium detector, which is cooled close to absolute zero, roughly around 10-15 millikelvin. And hence they are very sensitive to small temperature changes. When a dark matter particle transfers its energy to the nucleus, then it slightly and the recoil energy is deposited, it slightly warms up the detector. And then that produces vibrations of the crystal lattice or phonons. And these are sensed using superconducting tungsten transition age sensors. Now, the basic idea is that the resistance here depends on the temperature. So you are operating these at a particular temperature, which is near the critical temperature. Any change of temperature in the detector material will change the resistance. And then from the change in resistance, you can then get an estimate in steps about what is the recoil energy detected. It will be proportional. Now, since the detector material is semiconductor, it will also produce electron-hole pairs. And that is measured using a charge-sensitive amplifiers, which can detect charges. So SuperCDMS will detect the phonon signal and the charge signal. Okay. Now, let me come to tell you how it operated and what are the issues, and then I will tell you how we are trying to solve it. Now, here is a typical, the typical signal is you have a dark matter candidate coming, hitting the atomic nuclei, you have a recoil energy, and that is what you are looking for. That's the signal, okay? I can mimic it by using neutrons. So we have a detector in the lab, and you can put a neutron source, which could be here, californium. And then what you will measure when you measure the recoil energy as a function of ionization yield, it is going to lie here, okay, the green band. What could be a background is some particle comes, hits the atomic electron, and that also gives you signals. And if you take a source of that, such as barium here, then you get the signal here. If this background and signal are well separated, then, and you operate your detector, the detector looks like this, and the typical characteristics are given here, then you can discriminate. Now, if there are multiple sources of background, this background could eat away into the signal and your discrimination will be low. Now, SuperCDMS works in two voltage modes. So the voltage that is applied to detector is a low voltage mode, 4 volt. And that allows us for a very good signal to background separation, okay? However, the signal strength is small, so you lose out in terms of signals. So how can you gain it? because you are applying a detector threshold and you're cutting away some of the interesting signals. As you know, the signal lies in the lower energy part. So how can you increase it? You can increase the voltage. Now, when you increase the voltage, that amplifies the signal, and it amplifies through a very interesting effect called as Neganov-Trofimov-Luke, or NTL effect. So earlier we were trying to measure the recoil energy. Now you're measuring the total phonon energy, which has an additional amplification factor. Now, to explain in a simple way, suppose you have in vacuum electron and you have a potential difference of 1 volt. The kinetic energy gain is 1 eV. Now you have the same situation, but you have matter. Not only the kinetic energy is proportional to the voltage, but it is also proportional to the number of charges. That gives this amplification factor. So when you have an amplified signal, you also lose the discrimination, although you have an amplified signal. To probe low mass WIM, because you have a threshold, you have amplified the signal, it goes above the threshold, you detect it. So this is the dilemma. Good discrimination, low voltage operation, but if you operate in high voltage, then you lose discrimination, but you amplify the signal. You can probe lower mass. Now, we thought a lot about it. Is it possible to have a detector with both the features? That I will come to it in 1 or 2 slides, and I will tell you that's what we are quite excited about, that we can have both the features, and that would be a tremendous development. So let me show first the results, summary results of this cryogenic dark matter search. This is the cross section in centimeters square on the x-axis. On the other side is in picobarn. X-axis is the mass of the WIM. And the solid colored region is what is excluded. By that, what do I mean? Let's take an example. X-axis value is mass is 100 GeV. And you are here. The cross section is 10 to the power minus 43. It's ruled out. That means dark matter candidate of this mass with an interaction cross section of 10 to the minus 43. Remember the degeneracy which I was talking about? So this is ruled out. You can see these colorful islands. These are shaded, the shaded contours are where hints of WIMP-like signals are seen. So it's quite promising. And you can see all of them are clustered together at the lower mass region. Now, if you want to, this white space is what is unexplored. If you want to explore in this direction, as I discussed earlier, you have to increase the detector size and the time. And if you want to explore this region, you have to choose your detector material judiciously and decrease the threshold. And that's what the experiments are doing. I'll show you their limits, but before that, you can see this band, okay? This is the band coming from neutrinos, coherent neutrino nuclei scattering. Now, what is this? Now, if there is a probability that a neutrino can also scatter off the nuclei of the detector material. If it does, there is no way we can discriminate that event from dark matter event. So what I'm trying to say is that as the experiments probe, and if they exclude up to this, below this, they will lose their ability to tell whether the interactions were because of neutrino scattering of the atomic nuclei or dark matter. This is then called as the neutrino flow. There are experiments trying, it's such an important curve, there are experiments dedicated to try to measure this neutrino flow. This is the projections of how sensitivities, projections for different experiments. As you can see, the next generation or the experiments which have some of which have started to run can really push these limits much, much closer to this neutrino flow. and hopefully we will detect dark matter if it's there and if we are lucky. So this is a slide on the SuperCDMS snow lab. Here is its sensitivity in terms of WIMP nucleon cross-section as a function of WIMP mass. It can really go to low mass and look for dark matter candidates. This is a CAD drawing of the experimental hall. It has the shields, the dilution fridge, detectors will be kept, and all those other peripheral experimental requirements. The detector will again here also operate in low volt and high volt mode. The R&D for having combining the two, I will come in a minute. It will have germanium and silicon. Some characteristics are given here. It is expected to start taking data in 2023, and it is in one of the most deepest underground laboratory. Our idea is to gain experience working in these experiments and then utilize that to build up experiments in India if it's possible. So let me come to that novel detector. Remember, SuperCDMS operates in low voltage mode or in high voltage mode. Each has its advantage and disadvantage. But if we can combine the two, then it will be a unique feature. And we will operate the detector in low threshold, yet also not lose the discrimination. So what we did is with the Texas A&M group and using our dilution fridge, made a detector where the top region can be operated in high voltage and the lower region of the detector, silicon detector, can be operated at low voltage. And then we made these detectors and this was tested. You can see the details in this paper. We are very excited about the result because when we used a neutron source, that was what will mimic our signal, it's the red. And if you use the cobalt source, which will give us the background, it's the blue. And such a detector mimics very much the low voltage running, and yet we can operate it at low thresholds. So that is the exciting development from our group on this development of novel detectors. Now let me move quickly to the possibilities in India. One possibility where Saha Institute of Nuclear Physics and VECC and other groups are involved, and we are also involved, is possibility of looking at the Jadugoda Underground Science Laboratory to see if one can build up an experiment there. In terms of where it stands, in terms of overburden, it is here, and this was where the snow lab is. We had tried to see if our sensitivities that we get is comparable to similar experiments. This is, I think, the entry to the underground laboratory. In order to calculate the sensitivity, a lot of things are needed, which I described in the initial part of the talk. For example, we need to know the profile, the altitudes as a function of latitude and longitude. This was obtained using Google Earth because to get an idea about how high the overburden is, we need to know the rock composition to correctly do the Geo-simulations. And then we estimated the backgrounds. What we focused on is neutron backgrounds, both from radiogenic source and from cosmogenic source. And these are Geo-simulations where you try to mimic the experimental setup. We took as an example a cesium iodide type of detector and try to see how many neutrons reach your detector given all these overburdens, and there's some typical shielding also we put in. What we found that the neutrons which reach the lab from radiogenic source is of the order of 10 to the minus 6 per centimeter square per second. And cosmogenic source where when the incoming muons lead undergoes interaction, and that leads to neutrons coming in, is the neutron energy spectrums are shown here as a function of energy, the number of neutrons. And that rate is 2 orders of magnitude smaller, 10 to the power minus 8 per centimeter square per second. Using these and the equations which I discussed, one can find out only using this radiogenic and cosmogenic background. There are other backgrounds which we have not considered. But if you consider these dominant backgrounds, then one can get a sensitivity curve that how small values of WIMP nucleon cross-section and WIMP mass we can look at. And this is what it comes out, and turns out to be quite competitive with similar experiments at other places. But what we really want to do is occupy a cavern if INO comes up. It has been unfortunately on only planned stage. As far as I know, there were 2 phases, a mini DINO, a dark matter search at INO, and a phase 2. In terms of where DINO stands, it would be somewhere here compared to Snow Lab or compared to Sudan, the previous version of the CDMS experiment. What are the possible detectors? These are listed here. Some of them are being investigated in collaboration with BRC. And we are trying to gain experiment with with the experiments which we are currently involved. And if and when we get an opportunity to contribute to DINO, I think we are getting prepared to contribute there. So I'm coming to the end of the talk. Just before I end, I must say dark matter is a very important quantity. It is actually the fate of universe also depends on amount of dark matter. The current 25% level tells us that the universe will continue to expand. But we know that the universe is actually accelerating, and that brings in another interesting topic, dark energy. And that's not what I'm going to discuss, but I just wanted to share that dark matter is an important physics topic, which also plays a role on how universe will turn out to be in future. I will summarize the talk by saying that once it was thought that neutrinos cannot be detected, and finally they were detected. Many people said that the gravitational waves will never be detected, but finally they were also detected. Although it's 90 years and counting for dark matter, young people should join, because new ideas, especially on detectors, will help possibly detect them. And there are evidences which suggest that they exist. So that is all that I wanted to share with you, but I will take about 3 to 4 minutes to share with you a very interesting rap on the history of dark matter. I think the young people in the audience would enjoy it. Let me play this rap, and I think, let me just, okay, how to...
Yeah, you have to close this pointer.
Yeah, right.
Yeah, come to the normal pointer options.
Pointer options.
Or automatic.
Yeah. So I will, so what you see the text in the yellow color is what the rap will be. This is from Ohio Group. The contributor name is here. And on the right-hand side, I will be going through the history of dark matter, the important papers. So if young people read these lines, it's a rap, so, and enjoy.
My name is Fitzwicky, I can be kind of prickly. This song had better start by giving me priority. Whatever anybody says, I said in 1933. Observe the coma cluster, the redshifts of the galaxies.
Oops, sorry. Oh, I did a mistake. Sorry.
My name is Fritz Wiki. I can be kind of prickly. This song had better start by giving me priority. Whatever anybody says, I said in 1933. Observe the coma cluster. The redshifts of the galaxies imply some big velocities. They're moving so fast, they must be missing mass. Dark matter. Dark matter, do we need it? What is it? Where is it? How much? Do we need it? Do we need it? Do we need it? Do we need it? For nearly 40 years, the dark matter problem sits, and nobody gets worried because it's only crazy Fritz. The next step's not till the early 1970s. Astrophysical and Peebles, dynamics of the galaxies, hold its instabilities. They say if the mass was sitting in the stars, all those pretty spirals ought to be bars. Self-gravitating disks, oh no. What those spirals need is a massive halo. And hey, look over here, check out these observations. There are Rubin's optical curves of rotation. They can provide our needed confirmation. Those curves aren't falling, they're flat. Dark matter's where it's at. Dark matter, do we need it? What is it? Where is it? How much? What is it? What is it? What is it? What is it? And so the call goes out for the dark matter candidates. Black holes, snowball gas clouds, low mass stars or planets. But we quickly hit a snag because galaxy formation requires too much structure in the background radiation. If there's only baryons and adiabatic fluctuations, the Russians have an answer. We can solve the impasse. Yuhibov has shown that the neutrino has mass. So Lovitch tries pancakes, the dark matter's hot. Carlos Frank, Simon White, Mark Davis say not. Quasars are old and the pancakes must be young. Forming from the top down, it can't be done. So neutrinos hit the skids and the picture's looking black. The California laid back, Blumenthal and Freemax, they don't have a heart attack. There's lots of other particles. Just read the physics articles. Take this pretty theory that's called supersymmetry. What better for dark matter than the LSP? The mass comes in at a twiddle KEV, and that's not hot, that's warm. Jim Evil says, war, don't be half-hearted. Let's continue the trend that we have started. I'll stake out a position that's bold. Dark matter's not hot, not warm, but cold. The cold dark matter causes overnight sensations and weighty calculations, computer simulations, detailed computations of the background fluctuations. Results are good and the prospects look bright. Here's a theory that works, or maybe not quite. Dark matter, do we need it? What is it? Where is it? How much? Where is it? How much? Where is it? How much? We have another puzzle that goes back to Robert Dickey. Finding a solution has proven kind of tricky. The CMB's so smooth, it's as if there'd been a compact between parts of the universe that aren't in causal contact. Alan Guth says inflation will be our salvation. The smoothness of the universe, a causal explanation, and even make the galaxies from quantum fluctuations. There is one prediction from which it's hard to run. If inflation is correct, then omega should be 1. Observers say stop, no sorry, won't do. Check out these clusters, omega's 0.2. The theorists respond, we have an explanation. The secret lies in bias, galaxy formation. We're not short of critical mass density. Just some regions are missing luminosity. Observers roll their eyes and they start to get annoyed, but the theorists reply, there's dark matter in the voids. Dark matter, do we need it? What is it? Where is it? How much? Do we need it? Do we need it? Do we need it? Do we need it? Along comes Mochi Milgram, who's here to tell us all this dark matter clack has got you on the wrong track. You're all too mired in conventionality, wedded to your standard theory of gravity, seduced by elegance, general relativity. Just change your force law, that's the key. Give me one free parameter and I'll explain it all. Not so, claim Lake and Spergel et al. On dwarf galaxies, your theory does fall. The argument degenerates, it's Sunabar and brawl. Dark matter, do we need? What is it? Where is it? How much? What is it? What is it? What is it? What is it? You observations hit the theory like an ice-cold shower. They show that cold dark matter has too little large-scale power. Says Peebles, cold dark matter, my feeblest innovation. An overly aesthetic theoretical aberration. My theories must have firmer empirical foundation. Shed all this extra baggage, including the karyons whose particles we know, i.e. the baryons. Others aren't convinced, and a few propose a mixture of matter, hot and cold, perhaps with strings of texture. And nowadays, some physicists are beginning to wonder if it's time to resurrect Einstein's greatest blunder. Why seek exotic particles instead of just assume that the dark matter's all around us? It's what we call a vacuum. Who's right? It's hard to know till observation or experiment gives overwhelming evidence that relieves our predicament. The search is getting popular as many realize that the detector of dark matter may well win the Nobel Prize. So now you've heard my lecture, and it's time to end the session with the standard closing line. Thank you. Any questions?
Okay. Okay.
Very interesting. Very, very nice. Very, very creative. So at the end, so can we take some questions, Vedanga?
Yeah, sure.
Okay. As I said, there are lots of them. So let me first anyway go to YouTube and see how many we can take. Could sterile neutrinos be the candidate of dark matter particle? So this is Abhinav Chaudhary.
There are also suggestions for that. Yes.
Okay. Want me to move on?
Yeah.
Okay.
What I concentrated is only on weakly interacting.
Okay, fine. Then there is a question from Shiv Shankar. Sir, dark matter predominantly undergoes gravitational interaction, but are the laws of gravitation same for dark matter?
Okay. At the moment, they are, whatever I showed, we assume they to be same. And I think that's what was also done in the Millennium simulations, which you saw that what you saw here in the Millennium simulations, the dark matter distributions, the structure formations resembling the galaxy structure formation, the laws were taken to be similar. Yeah.
Okay. What if there is no new physics connecting dark matter and standard model particles? If dark matter interacts only gravitationally, we will never detect them, right? This is Jones' panicker.
I would be still optimistic, as you saw that WIMPs are those which do have weak interactions with standard model particles. So hence we do feel that WIMPs search has some promise. We have not yet excluded a large part of the cross-section versus mass. There are still hopes. And remember when we were doing Higgs search, it narrowed on to a small mass range. And so we should be optimistic search, and it's a difficult search, but we should do.
Okay, again from Jones, is the dark matter moving in and around galaxies, or is it still? How can we know it is moving if it is?
It's through the astrophysical observations. Somewhere I wrote the average velocity, I think 220 kilometer per second.
220 or 240.
Yeah. So
so that is also the next question. So are we also made up of a little dark matter? From Shiva Agarwal.
Difficult question. Since we are not able to detect them. As far as we know, we are made up of matter. Okay. Yeah.
Is there any expected mass and energy spectrum of the dark matter around us?
We do not have any. So that's why you see the sensitivity curves or the exclusion curves are as a function of mass of dark matter and the cross section. So we do not know. We do not know. We have, but what the experiments have ruled out, I have shown you to what degree. So And when I discussed about dark matter candidates, you can see the mass scale was huge and the cross-section scale was also huge. That makes the search more difficult. That's why I was saying if LHC gets a signature and that gives us a scale, mass scale, where to look for, that would make the direct and indirect searches more powerful.
Okay, more question taking you far away. Could string theory explain dark matter?
That I don't know, sorry. I have also not read about it. Sorry, this one I don't know. If somebody knows, can say. I also don't know.
Okay, there are some questions back here, so probably let us take them as well. Aditya says, does the interaction cross-section of dark matter depend on temperature and overall mass density, etc.?
Local, you mean the cross-section? Okay.
Yeah.
I have not, again, it's a model dependent. I am not too much into this theory, so I would not be able to answer now whether it depends. Yeah. So I'm sorry, I'm not into this theory, so I won't be able to tell you.
Yeah. One question, what is the typical mass ranges of WIMP that SuperCDMS experiment is going to look for?
Okay, I will show you, you can see for the SuperCDMS Snow Lab, you can get more details in this reference paper, and 10 GV to almost about 0.5 GV is what we are aiming for in different configurations of the detector. You see this dashed lines, and the range is in this x-axis, WIMP mass.
One question by Hardik, referring to your slide number 13, where you talked about, could you please elaborate about the form factor and why the reaction rate falls off due to that?
Let me see if I have the exact expression. Let's see. Okay, I do not have the expression here. So, yeah, well, you have to go into the details of the calculation. I thought I had, but I don't have it now. But if Hardik, you can send an email, I will give you the reference. If you are there, if you send me an email, I can give you the reference for that.
Yeah, sure. There are some questions again on the same Zoom. So let me go one by one because they raise their hands. So this is one is by Lakshmi.
Hello.
Yeah, please go ahead, Lakshmi.
Okay, sir. When we look at the events in for dark matter, do we also look at the event topologies, or we just look at the recoil energy or something like that?
We look at the event topology in the sense.
For example, like when we have neutrino interactions, we look for say shower-like events or drag-like events and so on. But depending on what type of detector is used, we look for those features also for dark matter.
Yes. The cryogenic dark matter search, it's a solid state. The detector is not as granular as what you explained to look at the shower shape or size. It's just the sum of the energies is what we try to measure. Of course, there are some partitions done, but those are used to discriminate the signal from background. As far as I know from last, whatever, 2-3 years of CDMS data looking at it, we do not use any such topology specific cuts to identify candidates.
There is a question from Rupesh Behra.
Yes.
Yeah, Rupesh Behra, please go ahead. Yeah.
So, sir, can you go back to the previous slides of the bullet cluster slide?
Bullet cluster.
What is your question?
So, can you explain it again, please? Repeat it.
Yeah, so what happened is two galaxy clusters, they came and collided. Okay. Now, when they collided and when they passed through each other, their speed slowed off. Okay. Now, each cluster of galaxy also has a hot gas. These hot gases also collided. As a result, they got heated up, and then when they heated up, they generated X-rays. And these X-rays you can see as this red blobs, okay? And these are close to the center of collisions, okay? Now, what people found is there is a cluster, mass cluster, much away from the center of interaction, collision interaction. What could be that? So it is something like some matter in that original colliding cluster of galaxy, which moved unimpeded and moved to that position. And that is what people claim to be dark matter.
So the blue ones are basically like those.
Yeah, these are the reasons we say that would be dark matters.
So how did you detected this particular region of that blue region?
There are, as I showed now, this depending on the mass, you would have different amounts of length, and so that's the technique dominantly to detect mass objects, and there are other techniques to measure X-rays. So it's a combination of many physical techniques to detect. One is lensing, another is light. That's all.
So another question.
Yeah, please.
So do we expect that dark matter have thermal properties just like normal matters? Like thermodynamical properties like temperature and
we still do not know what it is. The properties which I could know is what is listed here. Now, whether it has some properties, I don't know.
Thank you, sir.
So yeah, so we have a last question from Hariom.
Yeah, sir, you told this dark matter.
Okay, we'll also take another one after that from Tilak Ghosh. Yeah, please go ahead, Hariom.
Yeah, so sir, you told that the number of events 0.1 per kilogram per year, right? For this dark matter.
Roughly, yes, a rough estimate.
Yeah. So, sir, in this our ionoical, this is 50 kiloton. So, are we expecting more number of this dark matter events than neutrino? Because in neutrino events, we are expecting 10,000 event in 10 years.
10,000 events in 10 years. Yeah.
Sir, I am correct. Am I correct?
No, that number I don't know, Hariom, because that maybe Satya will be able to tell if the number is right or not.
The INO side, yeah, that's
right. Yeah, sir, that is correct.
We are talking about 3 or 4 events per day.
Yeah.
I see. Yeah, so then dark matter is more rarer.
No. So, no. So this is 50 kiloton, right?
50 kiloton. Okay. I see.
So it means we are going to detect more dark matter than like neutrino.
More dark matter than it. But that's not the detector which we'll use, by the way, right?
Okay, but okay.
No, that's not the detector which we are going to use. ICAL. That is not one. But this is the typical rate. So 0.1 events per year per kg. Yeah. And you are telling it is, so the rate of it is, you're saying 10,000 per kg per year. What is that per kg per year number rate for that?
Sir, this is 50 kiloton iron,
Oh.
and we are detecting roughly like 2-3 events per day as
2 events.
as we are, yeah. So so you can estimate like 50
It's 50
into 10 to the
million
power 6.
kgs,
Yeah,
right? 50
yeah,
million
15.
million kgs.
I see.
Yes.
Okay, now I have to think about it. I think this should be rarer, but
Yeah, this is coming quite high.
but this is standard number is 0.1 events per kg per year. That if you put in the, okay, I have to then look at it. So which one is going to be okay?
Tilak, you have a question. Tilak, go.
Yes.
Yeah.
Yes.
Hi.
Vedanga Tilak here. So what a nice presentation.
So thank you. Tilak, I couldn't hear.
No. I think there was a. Can you unmute again? Tilak.
Yeah.
Yeah.
Can you hear? Can you
Yeah,
hear
we can
us
hear.
now?
We can hear.
Yeah. Yeah. So Vedanga, the question was related to this in-beam experiment, like LHC, when you were talking about that charged particle can be detected and it can be a candidate. So what are those charged particle typical energies?
No. This LHC type accelerator search. So what in accelerator
Yes.
typically they do is you have 2 protons coming and colliding. You assume that in the interaction, dark matter candidates are produced. So what you do is you try, since the energy is conserved, you try to sum up all the energy of the particles produced and see if there is something called missing energy.
Okay, so missing energy. So you detect the missing energy.
Yeah.
I see. And what about this NISER detector? It's essentially a silicon germanium detector you talked about.
It's a silicon detector, yes.
And what did you make it?
No. It is actually made in with Rupak Mahapatra, and there was a MSc student, Himanshu Nyog. They are because honestly, we do not have fully that technology to make. What we did is with our dilution fridge, the measurements were carried out. You can.
So you have any publication or any article on that?
Yeah. So it's just starting. This is the reference here.
Okay, thank you.
Once again, Lakshmi has come back. I hope this will be really the last question. We already.
Okay.
Yeah. Please go ahead, Lakshmi.
So actually, this is because Hariom asked this question.
Yeah.
So for actually, our energy threshold is like 500 MeV. So that means we are detecting neutrinos which are above 500 MeV. But I mean, I don't know if I have understood wrongly or not. But to detect something, we have to have sensitivity to that energy region. But ICAL will not have sensitivity to.
Right. Our recoil energy are typically few kV.
So then we will not detect those kV dark matter.
Right.
No. He didn't really mean that we use ICAL detector to detect low energy, let us say, etc. What he was kind of little babbled is that just the event rate for INO for neutrinos versus the dark matter events, let us say in these CDMs. It's not that he used this detector to detect. I'm sure of it.
Yeah. He was talking about this number. Is it large or small relative to neutrinos? That's what.
Okay. Bedang, I think we have to take this question. Maybe a comment from Piyush Pani.
Yeah, please. Sir.
Hi, Piyush. Piyush, can you hear us?
Can you hear me?
Yes, yes, yes. Hello, how are you? Please.
Oh, hello. How are you?
Yes.
Hi, Bedanga. Nice talk. Okay. Yeah. This question about neutrinos in ion detector. I think it's a completely different thing you are talking about. This WIMP scattering on detector is a completely non-relativistic thing. Things moving with 220 kilometers per hour. These
That's it.
neutrinos that you are talking of in trying to detect in INO, these are atmospheric neutrinos. At GeV energies, these are completely relativistic stuff. Okay, so whole this is not applicable because and the cross section rises with energy like E square, so it's much larger. So you do expect a lot of these neutrinos will interact with ion, no doubt, but nuclear recoils will not be there. It
Will
will
not be
be
there.
some other way. Here
Right.
you are talking of nuclear recoils. So ion neutrino at such high energy coherence is lost and there will not be any recoil. They will just either deeply penetrating, inelastic scattering and other stuff. So, and first of all, also you can't detect those
Yeah, yeah,
recoils.
right.
Okay, so
Okay.
hopefully that clarifies.
Yeah,
It's
yeah,
completely different ball game.
yeah.
Okay,
Thank
you
you.
can't explain.
Thank you. Thank you, Piyush. Glad to hear your voice, if not seeing you.
Okay, no, I was very. Thank you. Nice
Okay.
to see you, Vedant.
Yeah, yeah,
Okay.
bye. Okay, I think Vedanga, you already spent an hour and a half or more on the lecture. So I think this time to, of course, there's still some questions left on YouTube, but I think we will not be able to take them to now. Hopefully somebody will answer them because they are, available as charts and comments. So I would like to thank you profusely based on, not only on my behalf, also from all the participants for taking time and giving a very, very nice pedagogical as well as, of course, very state-of-the-art kind of some of the experiments that you are and your group is, going to participate in a big way. And we wish you, of course, all the best. I also liked your slide about neutrinos and gravitational waves and dark matter all coming up in one slide. Yes, there is definitely more reason to think that, yes, why not the third one? And with that ray of hope, and so let us thank you once again. All the best for your future experiments. Thank you very much.
Thank you very much.
Yeah,
Thank you for giving the opportunity.
yeah, thanks. It's our pleasure. So just before I say bye, I just want to remind you once again, we have on Monday a talk by Ms. Mandakini Patil from TIFR. She's going to talk about programmable electronics and applications in high energy physics. As some of you know, that the electronics is now no more, it's a kind of prefixed logic that does repeatedly certain kind of things, acquire data and so on. Now the electronics itself has become programmable, which means after you put your electronics in the detector, you can make it work as a different circuit, especially on the trigger systems. They will do wonder in accelerator experiments. So she is going to kind of motivate why you need the programmable electronics and how they're applied as a main case study in the CMS experiment and in the upgrade. So it's a talk of different type that tries to kind of motivate you for the future needs of high energy physics experiments and how electronics and instrumentation takes charge of satisfying these requirements. So please join again back on Monday at 6 p.m. Okay. So thank you very much. Good night and take care and stay safe.
Thank you. Bye-bye.
Thanks, Vedant.